the mathematical description of the oscillation is given by a harmonic function like this. Okay, x as a function of t equals to xm. Okay, we can use sine or cosine function, it doesn't matter. Sine omega t plus phi. Okay? So this is the oscillation to describe one point. Like here, if I'm talking about the oscillation of this particular bar, okay, it can describe the oscillation of this bar. Once we use this as a source to initiate some wave, okay, so every bar is in oscillation. So each of them can be described by simple harmonic motion equation. Okay. By the way, since I'm going to talk about the oscillation up and down, let me use y instead of x. Okay. So I'm going to talk about the oscillation up and down. So let me use y instead of x. So this is for one point. Now, for each point, you will have a different oscillation. All these oscillations are the subsequence of the first oscillation, right? So they are related to each other. In fact, they should all of them should share the same frequency, or the period, or the angular frequency. We are talking about the same thing. So all of them have the same frequency omega, the same as omega for the source, the oscillation of the source. But they may have, and if there is no energy loss, they also have the same maximum oscillation position or amplitude. Okay. But what's different is that they have different phases. Because you can see, at the same time, some point reach the highest point, some point reach the lowest point. Some point is at equilibrium point, right? So they have different phases. If we organize this fact into one equation, this is the equation for one point. Now, if we have many points, so the function y should be a function of both position, x position, and t, time t, right? So this is a two-variable function to describe wave. Okay, so t means the time, x means horizontal position. So if we give some time, like say t equals to 1 second, so it's kind of frozen wave for t equals to 1 second. And yx will describe the position for different. Okay, so x equals to, like say, 1 centimeter, x equals 2 centimeter, x equals 3 centimeter. They will have different y. So that's a function of those different positions. If we fix position x for a particular position, then it goes back to the oscillation equation. It describes, like say, for x equals to 10 centimeter, it describes the oscillation of this point, particular point. Or x equals to 20 centimeter, it describes the oscillation for that particular point. Okay, so this is kind of you ensemble all the oscillation equation together, which is one variable function. Now we have a two variable function. Okay. Have you started to learn about the two variable function in calculus? Not yet? Okay. So for two variable function, you can also take the derivative, but then the derivative is called the partial derivative. You can take the derivative with respect to t, with respect to x. Okay, but now we're not going to talk about those things. We just need to think about the function itself, understand how does it, how it describes this wave motion. Okay, and it takes this form. if the oscillation to produce a wave is a simple harmonic function, it's like that, then the wave also takes a form of simple harmonic function, okay, sine or cosine. So, but here you have only one variable t here, and here you have k and t in this form. Okay. Now, let's look at the similar thing here. Of course, you can see here you have omega, the angular frequency. Here you also have the omega, the angular frequency for the wave. And we say that this is also the angular frequency for each of these oscillations. For the same wave, they share the same angular frequency. So when we talk about the angular frequency of the wave, it means that's the angular frequency for this oscillation, this oscillation, this oscillation, all of these oscillations. Ym, that's called the amplitude again, okay? So amplitude, Ym, same kind of meaning. And if there is no energy loss, okay, so all of them will reach the same amplitude as the initial oscillation. So like it's kind of to show that we have all the points, we have the same amplitude. Okay, so again, we have the same for the oscillation of the source and all the points along the wave. And okay, for the oscillation, once we know the omega, it can give you the, and then we can calculate the period and the frequency, right? Okay, they are actually talking about the same thing. Omega equals to 2 pi f equals to 2 pi over t. So for the oscillation, you can talk about the period and the frequency. And for the wave, you can also talk about the period and the frequency here. And similarly, when we talk about the period of the wave or the frequency of the wave, that means all these oscillations, all these points here, they share the same frequency, same the period. Okay. So wave is what we call the collective motion. When we talk about the wave, we will characterize the wave. We're talking about the common feature of all these points. Okay. The period of all these oscillations, the frequency of all these oscillations. But what's special for the wave is this quantity, k. Okay, this quantity, k doesn't have, this one doesn't have k for the oscillation of a single point. Okay. But before we talk about k, let's emphasize. To describe the oscillation, we call this, what do we call this? Phase. And similarly, we also call what inside of the sine function, whatever inside of the sine function, phase. This is the phase of the wave. Okay? And for the phase of the oscillation, it's a function of time t. So it basically says, if you have some object in the oscillation, it has different phase at different time. What do we mean by that? We mean that, okay, at a particular time, it's maybe in the valley. At another particular time, it's maybe in the peak. And then at a later time, in the valley, in the peak. Okay. Phase is basically talking about, is it in the valley, in the peak, or somewhere between or close to the valley? Okay. That's what we mean by phase. And for the wave, you can talk about phase, but it's a function of time t and x. So that means at the same time, at some point, same time, different point will have different phase. So at the same time, some point are in the valley, right, for the wave. Some point are in the peak. So this is the phase of the wave. Okay, they're different for different points. Now, we have a positive side and a negative side. That related to the direction of the wave. Okay. So if you have a positive side there, okay, negative side means the wave traveling to the positive direction of the x-axis. And the positive side means the wave traveling to negative direction. Okay. Please note that a negative side here means a positive wave. And positive side here means a negative wave. That's something you need to understand. Okay? Any question here? Now, we mentioned the wave has a quantity k here. Okay, again we use k. K is very common in physics. This is probably the third time we meet k, right? The first time we meet k is kinetic energy. The second time we meet k is a spring constant. Now it's also appeared in wave. Okay. K is related to an important quantity called the wavelength. Okay, you probably heard about the wavelength many times when we talk about all kinds of waves. But do you know what I mean by the wavelength? The wavelength is this kind of characterization. If you have a wave, it's oscillates like this way. Okay. Another wave, say, like this way, okay. So, either like this kind of big wave, or some smaller wave, like this, okay, not a crowd wave, okay. So, you can see from one peak to another peak, you have some distance for different waves. So this one is this large, okay. This distance is called the wavelength. So it measures the distance between one peak. Of course, you can also measure from one valley to another valley, or one center point to another center point. Similar. Okay, they will give you the same wavelength. So this is called wavelength. Now, wavelength is related to k. We can write the equation between the k and the wavelength as k equals to 2 pi over lambda. Okay? If you compare this, there's some similarity in this equation, but they're talking about different quantities. K equals to 2 pi over lambda. So K is the reciprocal of the wavelength multiplied by a constant, 2 pi. Okay, so it's proportional to the reciprocal of the wavelength. So physically, you can understand this K like this. First, we understand wavelength. A small wavelength means crowded peaks, right? Like that. A large wavelength means far distance between these kind of peaks. So increasing wave lambda, that means your wave will be from like this to this and this. Okay? Less crowded peaks in the same distance. And since K is proportional to the reciprocal of the lambda, so that means K increased in this direction, right? right? Okay. So large K actually means crowded wave like that. Small k means this kind of wave. Okay? That's the physical meaning of the k. And k has a special name. I always forget what's the name. Okay? We always say k. What's the name of it? Angular wave number. Okay? Because that's quite, this is very season meaningless name, so I cannot remember it. Okay? It's called the angular wave number. Okay. Now, I want to make some comparison between k and omega. So here, let's look at omega equals to 2 pi over t. K equals to 2 pi over lambda. And omega, these two quantities measures how the waves or the oscillation of each point repeated in time. The repeated pattern as a function of time. Okay. This quantity k and lambda, they also measure the repeated pattern, but it measures the repeated pattern along x direction. So the special repeated pattern. Okay. So basically, wave omega and t, they describe this factor. Am I going to make a fast moving wave or slow moving wave? Right? But on the other hand, you can see we can also make difference in terms of the spatial pattern. Okay? So I can make crowded wave. I can also make less crowded wave. Right? So they are talking about the repeating pattern for the time or for the distance. Okay. So but they have some similar relationship like that. And if you look at the graph here, I'm plotting the wave, okay, for a particular time. And then the wavelength lambda is the distance between peak and peak. But please note this graph and this graph. If this is time, this is y, this is y. This is time t. This is position x. So this graph, if we plot it for the wave, it will be a graph of the oscillation and for a particular position. Position x. And this graph is the graph of the wave for a particular time t. Okay? And they will look similar to each other. Harmonic function. But this, so if I measure this distance, what's that? In this graph, what's the distance between the peak to the peak? Wavelength? Phase?
Lambda.
It's okay. So we measure it along time axis. So it must be something has a meaning of time. Okay. In all these quantities we are talking about, which one has a meaning of time? No, frequency is not time. Who has the unit of second? No, hertz is not. Hertz is 1/second. Which quantity has the meaning of time? Period, right? P. This is period. Okay, we talked about this before when we look at the graph of the oscillation. This is the oscillation graph. And what's the meaning here? This is wavelength. Wavelength is something in meter. Okay? Length is called wavelength. It's some length. Period is the time for one cycle. It's some kind of time. So along time axis, you are going to measure the period. Along x-axis, you are going to measure the lambda. But the same thing here is that, what's this? What do we call this distance?
Amplitude.
Amplitude, Ym, and this is also amplitude, Ym. Because they both use the same y-axis, the distance measured from the oscillation. Measured from the center. Okay. So please compare the two graphs. Sometimes they will look exactly the same, but they're talking about different things. Okay. You need to look at this is y versus t for a particular x position. This is y versus x for a particular time. Any question here? These quantities are related to this graph. These quantities are related to this graph. Okay, in another word, this is if we fix the position and looking at the development of the motion as time change. And this one is we fix the time or freeze it. Okay. So look at different points. What is the motion? Okay. What is the position? Oscillation position at a different same place. Any question here? The wave itself gives you a very some kind of hint to understand the field. Okay. So it's a quite complicated description. We call it global description. When we're talking about the motion of the particle, this is so-called the localized description, and field is so-called the global description. What's the difference here is that a particle, at one time, it will occupy only one position. So you only need to focus on that position, right? The particle is here or here. But you see, when we talk about wave, that's complicated. We're talking about the motion of this point, this point, this point. In fact, when we talk about like an electromagnetic wave, we need to talk about the wave for the whole space. So every place there are something, every position in the space there are something in oscillating. Okay, and they have different phase. Okay, some like here it's in the peak, here is in the valley, here is in between. Okay, so you need, when you try to understand the wave, you have to imagine the motion throughout the whole space. That's global description. It's not just, you're not just focusing on one point here or there. Okay, all of them are an oscillation at the same time. So it's very quite difficult to understand, but in the modern physics, to understand the field and wave is very important. But to understand especially with electricity and magnetism, okay, you have to understand this kind of stuff. Okay, now one thing I would like to mention here is that we see that this is describe the repeating pattern for the time. This describes the repeating pattern for the for the position. Okay, and when I make this scheme, you can see that when we shows a fast or slow oscillation, or crowded or less crowded wave. There are some relationship here. When I try to make fast oscillation, what happens to the distance between peaks? It tends to be more crowded, right? So wavelengths tend to be smaller. When I try to make slow oscillation, can you see that? It's less crowded. The wavelengths tend to be larger. Can you see that? It's always so. If I try to oscillate it fast, the wavelength is small. If I try to oscillate it slow, the wavelength is tend to be larger. Okay? So there is some relationship related between these quantity, omega t and k lambda. In fact, they are related by the speed of the wave. Okay? Speed of the wave can be calculated either as omega over k. That's a fundamental equation. Wave speed equals to omega over k. And since omega equals 2 pi over t, k equals to 2 pi over lambda, you can say omega over k equals to 2 pi over t divided by 2 pi over lambda. So 2 pi, this becomes, so omega over k from the definition is always the same as lambda over t. Okay, so it can also be calculated as lambda over t. Since 1 over t equals to f, frequency, so this can also be written as lambda multiplied by frequency f. Now, you can see how they are related to each other. Usually, the wave speed for any particular system is a constant. It's a property of the system, wave speed. For this system, you have a larger speed. For that system, you have speed, another speed. For example, for the air, the sound wave in the air, the speed we know it's a constant. Okay, it's about 340 meters per second. So that's totally determined by the material, the system. Okay, the internal mechanism. You cannot change it by some external controlling. But since it's a ratio of two quantities, you can change one quantity. Then another quantity will change it accordingly. So you can see here, let's check if that makes sense. If I'm trying to make a fast oscillation, okay? So fast oscillation means larger omega, right? Okay. Fast oscillation means large omega. Omega is called the angular frequency, so high frequency oscillation. Now, according to this equation, for a large omega, to keep the same wave speed, what do we know about wavelength k? Should it be large or small?
Small.
Same V. Large omega, should it be large or small? Large. Okay, or you can write omega equals to Vk. So large omega means large k. Now is it correct? Large k means large lambda or small lambda? Large k means small lambda. They are reciprocal with each other up to a constant 2 pi, right? So large omega means small lambda. It's true. Small omega, slow motion, means large k. okay, less crowded. A small k, large lambda. So large lambda. On the other hand, okay, here, large omega also means small t. Okay, this is fast oscillation. For slow oscillation, you have large t, small omega. Small omega means small k. Or, oh no. This is small. Large k means small lambda. And large lambda. Okay. Please note these relationships, they are derived from these equations. So what do we mean by a fast oscillation? It should small t, large omega, large k, small lambda. Okay, slow oscillation, you have this kind of description. Okay, this is you don't memorize it. I cannot memorize because a lot of. But if you have the formula sheet, you should be able to derive it. Okay, from one quantity, then you get all other quantities. Okay, that's kind of practice for the logic. Okay, I think it's good practice. You can think about that. Okay, so that's a wave. Let's stop here.